Good morning, good afternoon, good evening, everybody. Welcome to today's Parasoft webinar on how to test avionics software for safety and security. My name is Arthur Hicken. I am the evangelist at Parasoft, and I will be your moderator and co-presenter today. And with me is Ricardo Camacho. Ricardo, how are you doing today?
I'm doing great, Arthur. Hi, everybody.
It's great to be here with Ricardo. We like to dive into various standards around different industries. Aircraft are always fascinating. Uh, these compliance issues can sometimes seem a little dry, but we're going to try and make it a little more interesting for you today. So again, thanks for joining us. There is a question box off at the right. So, stick your questions in. We'll handle them probably at the end, but queue them up as they occur to you. And after the webinar, of course, we will be sending people the usual, here's how to get the slides and here's how to watch the replay, etc. So again, thanks for joining us today. Our brief high-level agenda is, just talking about aircraft systems, right? This is not your father's aircraft, right? They used to say this is not your father's Oldsmobile or automobile, but things have changed. We're going to look at the Open Group Face Standard. We're going to learn how to face up to testing, and we'll do some Q&A at the end. So, once upon a time, aircraft were simple, right? If we look at this plane here, we see that there's, a half a dozen, 8 different things on the cockpit here, on the instrumentation panel, most of which are literally instrumentation. We don't technically need them to fly. They help us, but they don't do much. There's a couple of actuators here, right? We have a stick that help us control. We have a flap knob, etc. But it's a simple system, right? And simple things, not much can go wrong, which is really, really cool. But of course, in a modern era, we have lots and lots of different switches, dials, gauges, readouts, etc., because there's a ton of different systems in an aircraft. And in fact, even in modern jets, you may have noticed this in the background on the title slide, but in a modern jet, we have a wide variety of different kinds of things, from good old-fashioned buttons and knobs and levers to modern little digital readouts to full-on digital displays that can be multi-purpose. So at some point, they ran out of space to stuff knobs, right? If we look at the shuttle here, you can see that there are buttons, switches, knobs, and screens everywhere. And so these modern aircraft have to use things that allow you to dual purpose things, and always with that focus on what information does the pilot need at the moment that they need it. So it's even more critical in systems like modern fighter jets, where the systems are complex and they're full of lots and lots of software. Modern jet can have, 25 million plus lines of code in it. And typically the reaction times become very, very critical because the hazards and risks for a fighter jet are much higher than that for a passenger jet, in the sense that somebody may be chasing you or shooting at you. And the most modern system that I've really kind of seen, and apologies to anybody who has a cooler aircraft than this, right? But this is the Dragon capsule that launched a couple weeks ago. And it certainly is a high-end aircraft with lots and lots of code in it and does a shocking amount of stuff on its own. But it's cool because they have these giant heads-up displays and touch displays here, where this display changes dynamically based on the needs of the pilot and co-pilot. So it's a really, really sophisticated system, but it hasn't overloaded the operators by having too many devices in it. So it's pretty cool that you can certainly watch this on the SpaceX site, watch these people control this particular system. It's fascinating. Now, the systems in an aircraft have become very, very complex because they're taking over more and more and more of the operations of the craft, right? So it's engine, it's cabin, it's the wheels, landing gear goes up and down. Once upon a time, it was always down, right? We have a variety of systems in the cabin. We pressurize them now. We have temperature control, which is actually critical. We're monitoring fuel systems for leaks, for proper fuel consumption, engine temperatures, all kinds of things going on in the system, trying to keep track of exactly what's going on. And of course, it's a little different in every single aircraft, right? It's not that aircraft are built one by one, but particular models of aircraft are really built one by one, and they're really quite unique. And on top of that, we have to think about what can go wrong in these complex systems. And so we have to look at, well, what happens if, this particular sensor gets a bad piece of data and tells us that we're too low or we're too high or we're too fast or we're too slow? And what happens if it gets a wrong piece of data? What happens if it doesn't report any data? And so there's a variety of circumstances that we have to make sure. And it's funny because developers who are new to avionics systems might be used to what we like to call the happy path software, right? We look and say, okay, well, the sensor says this, right? And everything is good. And we'll do a high number, we'll do a low number, and we're good. We do a happy path and a couple of less than happy paths. But when we're doing avionics systems, we have to really think hard about what are all the possible use cases and what do we do when these things happen to make sure to maintain the safety of the aircraft and the people on board. So we have to think about what can go wrong, and that starts with identifying various failure modes, right? We have to sit around and think about what can go wrong. And this requires a healthy paranoia. We really have to go, okay, well, if the temperature's high, if the temperature's low, if it's wet, if it's dry, if we're fast, if we're slow, if we're overloaded, if we're underloaded, if we're underloaded but a full fuel load, if we're overloaded and a full fuel load, and all these kinds of things. And the broader knowledge that we have, the more rational experiences we have to think about what can go wrong. Once we have a big list of things that can happen, then we start to look at, okay, well, what happens if this happens? If I go back to my first aircraft and I lose my airspeed, in a plane like that where there are no windows, I'm sitting outdoors, I can probably judge airspeed. It's probably not critical to me. But in other aircraft where I can't see the outside at all, or it's difficult to see, or I can't see down, it may be very, very difficult to judge airspeed. And the higher airspeeds are, much more critical to me than an aircraft that flies at 50 or 60 miles an hour. So we have to think about what's the severity, how likely is it to occur, what does it take to make it occur, and will we notice if it occurs? If I'm leaking fuel or my fuel tank's low or I have an oil leak, will I know before it gets critical? On cars, really cool cars, good cars, I would say have like a rich set of instrumentation on the dash, and they tell you things like the temperature of the engine, as well as maybe the temperature of the oil and the oil pressure. Other cars have what they call dummy lights, and the dummy light tells you that something bad happened, not a warning that something is happening. So there's really nothing you can do other than it happened. And detectability is really about that. Can we notice that something is in a bad state early enough to do something about it? And then, of course, we have to prioritize, right? We have to look at the probability. Will this happen? How likely is it to happen? And if it's likely and it's dangerous or severe, we have to start looking at mitigations. What can I do to make backup systems, secondary systems, early warnings, or to make it easier to respond to the issue, redesigning systems so that failure modes are easier to operate? Or are there things I can do in the design to literally make the thing less likely to occur? Or again, make the severity a lower number. And so we've seen in aviation over the decades, as we've changed materials in the seats and we've changed instrumentation, we've changed procedures. So we constantly try to make air travel safer and safer and safer. And it absolutely is. If we compare it to other modes of transportation, it's really, really good system. So as we think about like what can go wrong, one of my recent fascinations is YouTube videos that show these airports that have pretty severe wind shear going on, and the winds are coming from the side, and sometimes it looks almost like a VTOL aircraft coming in, where we see the plane coming in canted to the direction of the runway at maybe 45 or more degrees, and then it looks like it's really not moving. The forward motion is nearly zero, even though the engines are cranking, and it kind of sets down and then quickly tries to orient itself. And And if you watch a bunch of these videos, you'll see quickly there are a few airports that show up over and over again. And I kind of put them on my reverse bucket list for places not to fly to. But that's one of the things. Weather's always an issue. And again, I watch a few aircraft safety channels on YouTube that talk about, what went wrong and what can happen. And weather's just a common issue, whether it's a large aircraft or a small aircraft, and very frequently with small aircraft. But, from wind to water interfering with the jets to, lightning strikes, which is typically a pretty nasty thing for electronic systems. They tend not to like it. There's a variety of things that can happen that you have to think about. And of course, as we start to add more and more computers on our desktop, we're used to looking at the blue screen of death, but we really don't want to see that blue screen when we're in flight. And in fact, a few years ago, when one of the issues I'll be talking about in a moment came up, I started calling friends who were pilots and who were journalists in the aviation arena and asking them about blue screen of death type issues. And it was shocking to me, the anecdotal information that people had about how frequently computers needed to be rebooted in flight. And one of the big banes of this is really the overflow category, right? Buffer overflow, numeric overflow, clock improper synchronization, and things like that. And that was one of the big issues, was these kinds of buffers being messed up and causing a problem at a specific time. And we'll go more into that in just a second, but I want to talk about it because these buffers are really a constant issue around software safety, software security, software reliability. And in fact, I have these little bubbles on the screen. If I look at buffers, they're that center thing, right? And in fact, at the software level, when we're writing code, when we're testing code, when we're looking at coding standards, the overlap between the safety, security, and quality bubble is much, much higher than what this picture represents. It's very, very high. When I fix a numeric overflow, I'm fixing a reliability problem, I'm fixing a safety problem, I'm fixing a quality problem, I'm fixing a security problem, all with a single fix. So as we look at these buffer issues, right? I remember the Dreamliner issue of a few years ago, and they had a couple back-to-back issues around having to reboot the system after a certain number of hours and days. And when you calculated the number of days, typically you can find number of hours and number of seconds that suspiciously align with hard-coded limits in computer systems. And the interesting thing is that if you're worried about, overflow, underflow, overrun, improper reads, wrapping around the dial on an integer, right? When you have a max value of 128 and you went to 129, which is suddenly 0 again. There are software engineering coding standards that work well for this, from those in MISRA, those in CERT, those in the Joint Strike Fighter program, and things like that help you not just detect these things early, but actually code in such a way that they can happen. So, just some examples of this happening over the last couple of decades. There was a Patriot missile defense system that had to be rebooted every 8 hours, which is, an indication of a very small numerical value, right? That, a very small number with a very small max value to get that frequent of a reboot. But in a defensive aircraft, that's kind of an annoying thing, right? Like I don't want to reboot the thing 3 times a day. That seems kind of problematic. Airbus A350 had an issue where it had to be rebooted every 149 hours. I didn't do the calculations to see exactly which particular kind of overflow it is, but the Dreamliner one was just fun because if you calculate the 248 days times the 24 hours times the 3,600 seconds, which is the number of seconds in an hour, right? Like 60 times 60, then you get this 21,427,200, right? Number, and a maximum 32-bit signed integer is 21,474, right? Like we can see that if we had gone 249 days, we would have passed that maximum integer, which is why the reboot every 248 days. So that's why I say, like, I'm uncomfortable with reboots or other issues in a system that occur based on magic numbers. I'm always suspicious that there's an overflow in place. And while the short-term fix is the reboot, I really want to know, where is this number and why is it happening this way, and what can I do to make this not happen, to mitigate this problem, right? Like that's really the issue for me. There's a funny quote in this blog that I reference for some of these aircraft systems, and he says, I encourage you to change all your data types to Boolean. Whenever there's a data quality issue, it can only be wrong by 1 bit. And I laugh tongue in cheek. I am known as the code curmudgeon, so these kinds of statements really make me happy. But from an avionics perspective, that kind of is what you're supposed to be doing at a testing level, is not just looking for problems and then fixing them, but asking yourself, was there a different way to represent this data so that this kind of an issue can't happen? So I'm not actually encouraging you to change all data types to Boolean, but I am encouraging you to think twice when you're coding about, when you have a number and saying, what's the biggest value this number could ever get? And do I need to worry about it? And should I use a bigger number, right? So that I know, can I use an unsigned int where I can go much, much longer period of time? Things like that. Magic numbers can really get you. Another area that probably doesn't get enough attention, and I would say in avionics is way more critical than a lot of other areas, is UI, right? Like if my word processor has a bad UI, I'm annoyed, right? At worst, or maybe you lose me as a customer. If my aircraft has a bad UI, this can be difficult to fly, difficult to learn, difficult to come up to speed on a variety of aircraft. But also the problem again is when something bad is happening, I have to respond much more quickly. I have to make decisions. I need suddenly way more data, and then I have to do whatever I need to do. There's these long-running jokes about Boeing versus Airbus, right? That if you go and Google Boeing versus Airbus memes, you'll find hundreds or thousands of them, right? But the Airbus systems are advanced and use a smaller number of items in the user instrumentation. So in theory, it's easier to understand, easier to learn, easier to fly, and easier to respond to an incident because it is critical. There is an issue where, you can oversimplify things and maybe run into a problem. There is a funny story. If any of you have watched the movie Apollo 13, for those who aren't familiar, the Apollo 13 had an explosion in a fuel cell after takeoff, quite a while after takeoff, after their injection burn, and they had to mate the lunar module to the front of the service module so they'd have more air, have a better CO2 scrubber, and have some more fuel to do control systems, etc., so that they would survive long enough to get around the moon and slingshot back to Earth. And then at the end, of course, they had to get rid of it because the lunar module was in the way, and it offset the built-in software on the system that understood how to perform a reentry burn, but not with a lunar module attached. So they had to eject it, but of course they had been living in it. So of the 3 astronauts, Jack Swigert was still in the command service module, and he had this checklist that they'd given him for exactly what to do, and that's great. And at the end of the checklist is to press this button that, disconnects them from the lunar module, right? We eject the system and move away from it. And if anybody's in the module at that moment, they're going to die. And because they were extremely cold and they were operating on low oxygen, he was nervous and he didn't want to press this button at the wrong time. And so this isn't precisely how it looked in real life. This is, from the movie, but he took a piece of duct tape and taped a piece of paper over the button to perform the maneuver and wrote no on it so that he couldn't accidentally do it. And this is one of those things in UI, right? Like we don't want it to be too simple to do something dangerous, but we don't want it to be too hard to do something dangerous when the moment is critical. And just one other in this area, Air Interflight 148 near Strasbourg, France in 92, Airbus 320, which is one of the most advanced cockpits in the world at the time, had a lot of digital instrumentation. And the problem is that much of the instrumentation had two modes. And this is the problem with these, we're going to try and put more data into a smaller area. Therefore, we're going to show you different things at different times. And if you look at that upper right, there's a little thing about your descent. And sometimes that number is showing you the angle of descent, and sometimes it's the rate of descent. But it uses these funny decimals and lets you multiply. And what had happened in this case was that the captain set a descent. He thought he set a descent angle of 3.3 degrees, but what he actually had done is set a descent rate of 3,300 feet per minute. And because of the dual mode display, he hadn't noticed it. And because of that, the aircraft ended up being lost with, a lot of the passengers as well. So it's just one of those cases, right, that if things can be mistaken, it's dangerous. And again, with aircraft, when they're under stress, when you're in the middle of a hazard, when a risk is, raising its ugly head, that's the moment where you're most likely to make a mistake. And so it's super, super critical that these systems are very clear and obvious and operate properly at that moment that you need them to. So this brings up an issue about, like why face? We're going to talk about face today, right? And why does it matter, right? And one is the issue of complexity, right? Again, here we look at, and I think this is a DC-8, if I'm correct. And you see just you can't fly this with one person. You can't fly this with two people, right? Like 3 people is what it takes to fly the thing. And you think about all these systems coming from various vendors and being plugged in together, right? We like to joke that, pull stick up, plane goes up, push stick down, plane goes down. But these buttons all have value, right? And these gauges have meaning. And at certain times, they're very, very critical. And they have to work together properly. We can't have one system messing up another because of voltage issues or not operating properly, etc. So again, it's funny when I think back on automotive, because there was a time in the not too distant past where every car model from every manufacturer used fundamentally different sets of parts. And so when you'd see recalls occur, you would see that, carburetors were only used in a few models of vehicles from a single manufacturer. And in the last, 10 years or so, we have seen some pretty big recalls hit the automotive industry because of the large amount of reuse, people using components over and over. So, there's a downside to it, but there's an upside to, how quickly can we produce the components? How much does it cost to produce components? How quickly can we assemble components? What does it take to be, checked out on a new aircraft? Because it has the same components, it's easier to understand, less mistakes, etc. And so it's really, an attempt to make it easier when someone climbs into an aircraft to understand what everything is and where it is, as well as make it easier to build and test reliable aircraft systems. I really do love this picture on the right. Ricardo and I have been laughing about it since I came across it, right? It's on one hand, it's quite silly. Like on the right, there's a weird looking mouse button or a label there, but it's also like there's things like, enemy radar to see other planes, right? Cloud radar, it's actually very, very useful that it's explaining systems to people. And that's part of what, is important. The face standard when you look at the overview to it, tells you that the lack of common systems and standards among aircraft platforms has decreased interoperability, which increases development integration costs and development cycle time. So face is meant to improve that. It should improve development time. It should decrease costs. It should improve quality and reliability as well, because we have the same part over and over and over and over, and we can really make it perfect. So with that, we're gonna dive a little deeper into the standard, and I'm going to turn things over to Ricardo.
Okay. Thank you, Arthur. That was fantastic. And I really do love that image with go fast, set the brakes and stuff like that. Okay, so I'm going to be talking about face and, kind of put things in perspective as what's kind of going on in the industry. So really within the past 11 years, there has been a strong commitment by aerospace companies and our U.S. military forces, or really the Department of Defense, towards reducing the cost of developing, delivering, and maintaining avionics systems, including having these cost savings propagate into future avionics systems for the purpose of not just cutting costs, but also having a quick turnaround in updating and upgrading them, and again, in current and in future aircraft. And by aircraft, I'm talking about all different types. So these, the face is supposed to talk commercial, military jets, bombers, transport planes, attack helicopters, drones, UAVs, and much more. Now, Arthur showed you a great set of evolution images of avionics systems, and to reiterate the complexity, today you have multiple components that make the whole. You have engine controls, flight control systems, and navigation, communications, weather radar, flight recorders, lighting systems, fuel systems. You will also find threat detection and mitigation components in military aircraft, like infrared or electro-optic systems for tracking targets and countermeasures, and systems that carry out hundreds of other missions and flight management tasks. Now, imagine having to design these systems for every different type of aircraft. The cost has been increasing in an exponential rate, which makes future avionics systems unaffordable. So I'm going to talk about the Open Group Future Airborne Capability Environment. So FACE is the acronym. It's a solution that continues to be adopted by multiple military projects. To give you a little history, the FACE Consortium was formed 11 years ago, and it's sponsored by all the U.S. military branches and primes like Boeing, Lockheed Martin, and Rockwell Collins. You will also find principal members like Harris, GE Aviation, BAE Systems, and others. I'm actually really happy to announce that we joined the Open Group FACE Consortium. So Parasoft has joined as an associate level member, and we are looking forward to contributing to the development of the FACE technical standard. And Parasoft, being a software test automation vendor, we are working on offering solutions to help with the test and development of software components or units according to the FACE standard. Now, I'll be presenting a slide on what Parasoft has actually started to build, and we demoed it at the FACE Technical Interchange meeting that we actually just had about a couple weeks ago in Huntsville, Alabama. It was hosted by the U.S. Army. Now, I'll be going into more detail on the FACE standard, but note that it is different than a process standard like DO 178C. In fact, because FACE addresses flight software, it by default needs to be compliant to DO 178. The FACE standard, however, exists for the purpose of delivering avionics software units that are portable and conform to the FACE open architecture, making the units transferable and affordable. So there are aspects of the FACE approach that address not just the technical practices, but also the business process to incentivize the industry and procurement of these portable units of conformance. Now, I've been using the term unit, and FACE defines UOP, or unit of portability, to represent software components that have been certified to conform to the FACE standard. They also interchangeably use UOC, or unit of conformance. So based on what the messages you're trying to convey, whether it's portable or whether it conforms to the standard, you use UOP or UOC. So that's just some interesting stuff to be aware of. Now, this is a chart that the FACE Consortium uses to show the unaffordable trend that we were in building modern avionics, and also the trigger that sparked the birth of FACE. As you can see, the cost to develop, integrate, and maintain software continues to grow at an exponential and unsustainable rate. Now, GE's Common Core System, CCS, changed the approach in developing avionics. It provided the much needed revolutionary course that reset the cost complexity curve for the 787 and increased in productivity. This modular and open architecture design of the system allows the operator to change or upgrade software applications as they see fit without requiring the developer to reset, to retest, or recertify the entire system. Now, the Boeing 787 avionics would have been impossible without, unaffordable really, without the revolutionary concept that GE brought in. And so the U.S. military and the DoD took notice of this efficiency and found it necessary to utilize and commit to open system standards, tools, processes, and also business model. So the DoD objectives are not just affordability, but speed and being able to quickly deliver new or updated software and hardware components, which requires agility, and it has to be safe, secure, and of course of high quality or excellence. So these objectives expand beyond software. It needs to include hardware and an architectural strategy, not just technical, but a business strategy as well. So therefore, in order to establish this common operating environment, there is a collaboration between the DoD and a couple of open group working groups at the moment. You have the Modular Open Systems Approach, MOSA, which is a DoD integrated business and acquisition strategy, including having a technical modular architecture design strategy to build and achieve a competitive and affordable avionics systems. Now, avionics are comprised of sensor systems, an assortment set of signal processing hardware. You have sensors, computers, and other aspects that deal with communications, cyber security, reconnaissance, surveillance, intelligence, and command and control. Now, these are integrated through the Open Group's Sensor Open Systems Architecture, or SOSA. So when we have these face team meetings, SOSA will usually always be there. Now, and then you have FACE, the Future Airborne Capability Environment Standard, there to provide conformant software units of portability that are safe, secure, modular, and scalable. So this is the DoD's collaborative view in obtaining these objectives. I like visuals, so actually in my next slide, we can actually see the evolution of this architecture. Now, on the left-hand side, we see the individual set of aircrafts or platforms. Again, remember Arthur talked about all of these different types of airplanes, and I'll refer to them as platforms. And the traditional approach is, to develop unique hardware, unique software and hardware to integrate these avionics components into those platforms. Then this typically can take, 18 to 33 months. Now, on the right, we see the use of a common operating environment to enable reuse and interoperability across multiple platforms. Hopefully, this visual puts it in perspective, but as you can imagine, the savings are huge. Now, all right, so let's actually start diving into the FACE architecture. Now, this diagram that you see here is from the standard. This is the FACE architecture diagram with the segments. So you're seeing the architecture as it's being defined with the various segments and connections. Now, each segment has its purpose, and within each segment, software units, certified FACE UOPs or UOCs, run or execute. And I'll go into the software certification process actually later because that's kind of interesting. Now, also for each segment, there are a set of FACE standard requirements that must be satisfied. And I'm going to actually show you that through a spreadsheet that exists. Now, starting from the top, you have the gray background illustrating the operating system segment, or OSS. The OSS can host various operating systems, such as the Wind River VxWorks 653 and the Wind River Linux, and there are other offerings from Green Hills, DDCI, and DonnerWorks. Now, these are certified FACE UOCs. The portable component segment hosts software components that provide logic capabilities, which are not tied to any data transport or operating system, such as Collins Aerospace Mission Flight Management Software or localizer performance and vertical guidance calculators. Now, the transport services segment is comprised of communication services. So data distribution and capabilities that include routing prioritization, addressability, transformation, persistence, and much more. RTI's Connects TSS is one example of an available UOP. Now, the platform-specific services segment is comprised of three subsegments: device, common, and graphic services. They provide services such as management of data and translation, logging services, streaming media, health monitoring, graphics processing, and much more. An example of a UOP is Honeywell's device driver to convert raw 1553 data messages into a face data model. Then the input-output services segment provides the abstraction of the interface hardware and drivers from the platform-specific services segment. Anyways, these are the face segments in a nutshell. Wish we had a lot more time, but we don't. So anyways, however, you have probably noticed several green horizontal lines in this image. Now, these represents the face standardized interfaces. These are face interfaces that provide the connection between the face architectural segments, and they are defined in the technical standard, and actually they're provided in IDL format. For example, the interfaces between PCS and TSS segments are data type specific and can move data between each other, and it can be blocking or non-blocking types of messages. Now, there's a lot of technical detail in the standard for each of the segments, which we, again, don't have time to go into, but you can freely download the technical standard and look at the details. Also, consider joining FACE if you're developing software for avionics systems. So I'm going to actually now talk a little about the certification that I've been mentioning about. Now, FACE has the Open Group FACE consortium has a well-defined conformance program and process for software suppliers to follow. First step is for the software supplier to submit a unit of portability to the verification authority. They perform the verification, the verification authority performs the verification activities, and then this involves using a conformance test suite, which actually I'll be also talking a little bit about. And then if the unit of portability receives a passing verdict by the VA, the software supplier can then submit their verification results package to the certification authority. The CA then assesses the verification results packages, manages legal agreements, and issues a FACE conformance certificate. The final step is registration. The software supplier can submit the FACE conformance certificate, the UOP's description and metadata to the FACE library administrator, who reviews and confirms the FACE conformance certificate, and then publishes the existence of this UOP in the FACE registry for it to be procured. So let me give you a quick view of what that registry looks like. You can see here it's a website. It's open. The registry site is, again, where companies can find FACE units of portability for purchase. The software itself is not located there. Only the description and contact information is provided. The interested party can reach out to the company and go ahead and decide to procure that piece of software. Okay. Now, the other thing I want to talk about is that besides the standard, there's a lot. The standard itself, if you look at the latest version, is 3.1, the FACE Technical Standard 3.1 edition. It's 564 pages. And there are several supporting guides and tools to help folks with the development and delivery of these UOPs. There are guides like the FACE Software Supplier Getting Started Guide, and there are tools like the Conformance Test Suite or CTS. And there is the Conformance Verification Matrix, which is actually pretty cool, and I'll show that. So there's a lot of useful and important help tools and stuff available for you. Now, these guides and tools can be found online at the Open Group Library. And actually, let me go ahead and introduce you also to the CVM, the Conformance Verification Matrix. It provides the requirements defined in the standard for each segment, but it's in the Excel spreadsheet format. So you can easily filter the requirements for the segment of interest. These requirements need to be satisfied, and there is a column to include the artifacts to show proof of fulfillment for each requirement. Now, the CVM is meant as a tool to help users obtain conformance, so it's not a substitute for the actual standard. So what I'm going to do is I'm going to actually navigate into the spreadsheet to kind of show you this. So you have, everything has a unique ID. You have all of the sections, and you have the B column here, whether verification is needed or not, and then you have the face segment that you're interested in. So for example, if I'm interested in providing a PCS software unit component, I can go ahead and click OK. And you can see the unique IDs. You can see that these are all of these elements here. All of these are requirements that need verification. And again, the face segment that I'm building my piece of software for, in this case, is the PCS. So it says here, for example, for number 1, the PCS UOC shall only use the interfaces defined in section 3.2 and 2.8 and so forth. And so how do you verify that this requirement is going to be satisfied? Well, there's a verification method, and you can see here it says test. The conformance artifact is a test suite. So you have to use the conformance test suite and to exercise your code through it. And once you have that output, you can use it here as the software supplier artifact that proves that you've satisfied that particular requirement. There's also some verification notes available for you, and there's also some maybe additional requirements, conditional requirements as well. So there's different kinds of verification methods. There's inspection. You may need to provide a unit of conformance design spec. And there's also per reference section. So if you go into the section, this particular section here, you can find 3.2.5. You can find additional information regarding what are the artifacts that you need to provide. So this spreadsheet, again, is used to help you make sure that you know all of your requirements in order to fulfill the standard, and you can fill these out. All right. All right. So anyways, that's kind of what I wanted to show you in regards to the standard. So I'm going to stop sharing here. Let's go back to the standard. We're back at the slides. Okay. And what I want to show you now is the conformance test suite. So again, the face conformance test suite is a configurable tool where you create a project. You set things up to mimic the target ecosystem, and you can then run the conformance test. Part of the test includes performing a build to verify the correct usage of the APIs defined in the face technical standard. If it compiles links and builds against face libraries, it's a pretty good indication that your software unit is face conformant. Now, the tool is free to download to test your code against, and you will want to do this before you submit to the verification authorities. Also, there are various versions of the face standard. Therefore, there are corresponding CTS versions to match. Here you're seeing the current 3.1 CTS on the left and an older 2.1.1 version of the standard and the CTS on the right. Now, Parasoft actually prides itself in supporting the software development industry with its software test automation offerings, and I see several opportunities in supporting the face standard. So actually, one of the things we did is that to help support our customers, because we do a lot of support for MISRA, AUTOSAR, CERT, we do unit testing and much more. But for face, we started to create a face code analysis configuration. So this is a snapshot of Parasoft C++ test, and what we demoed at the face technical interchange meeting a few weeks ago is this actual configuration, which what it does is it searches for face coding violations like improper use of restricted POSIX functions for each segment, including the use of old POSIX functions like sprintf, which poses security concerns, and they promote to use snprintf instead. And also identify certain POSIX enumeration values that should not be allowed. Now, we intend to promote solutions like this and other solutions that we are considering as well for help customers and folks achieve face conformance and help automate that whole process. Now, for example, we also have this Parasoft DTP. This is our extensive analysis and reporting dashboard, which can monitor the health of your software, reveal code quality metrics, tell you how your unit testing, system testing, code coverage, and other these testing methods, how they're performing. We also have capabilities in requirements traceability, where we can trace from requirements to test cases and down to the code, and show you the progress towards conformance or compliance to standards like DO 178C and much more. In fact, this leads me to the next slide. As I previously mentioned, Avionics software also has requirements from process standards like DO 178C or B, and which are very different than, as you're probably now aware, than FACE standards, than the FACE standard requirements. Now, for DO 178, some of the key challenges are requirements traceability, managing for compliance objectives, compliance to coding standards, on-target hardware validation testing, code coverage, including at the object level, and the tool used needs to be TÜV qualified. Now, Parasoft is in the game to help ensure FACE conformance. And actually, one of the other things is, Arthur and I do these webinars, and we've done one on DO 178. So actually, at the end, I'm going to provide a QR code to help you, show you how to get there. But what we do is Parasoft provides solutions for the whole software development lifecycle. And I'm going to provide you a quick view of the Parasoft V model to give you a high-level understanding of the solutions that we offer for each of the phases in the software development process. Note that we also have integrations with solutions like JAMA, Codebeamer, Polarian, and others, which complement or help fulfill many of the DO 178 requirements. Parasoft supports DO 178 and DO 330 conforming qualification process with our automated tool qualification kit for all DAL software levels. And on the right-hand side of the V model, we have a plethora of solutions in the verification validation of each development phase. Now, starting with static analysis at the very bottom in the implementation phase, and then as we move up into unit testing, we have solutions for that, and all the way on up the V model. Also, take a note of our Parasoft SAW test for functional API testing. I see huge potentials here in testing phase software units. All right, looks like we're getting close to running out of time, so I hope that the glance of the FACE standard was very educational. And feel free to reach out to Arthur or myself. You can also send us an email at info@parasoft.com or follow us on LinkedIn, Facebook, and Twitter. I highly recommend that you visit our website. We have tons of great informative content, including these QR codes, where the first one will take you to a demo of a video of Parasoft C++ test, and you'll see it in action. And we also integrate into lots of your IDEs. We'll probably integrate into your existing IDE. And also, Arthur and I, again, delivered a DO 178 webinar, which I think you'll find very informative. And if you're going to also be at the Aerospace Tech Week in Toulouse, France, on November 3rd through the 4th, please come by our booth, the Parasoft booth. I will be there, and I'd love to see you. All right, so we're getting real close to time here, so I'm going to open things up for Q&A.
All right. Thanks, Ricardo. Yeah, we had a couple questions come in real quick. We'll take what we can. One was, are there military projects in the U.S. using FACE architecture?
Yes. The one that quickly comes to mind is the U.S. Army's Future Attack Reconnaissance Aircraft. Now, this is Bell's Invictus 360 helicopter. Bell is designing their data concentrator unit, a DCU, in accordance with the FACE standard. There are also several members of the FACE consortium that have been selected by Bell, such as RTI, TestSavvy, DDCI, and others. So if you go to the Open Group website, www.opengroup.org/FACE, they have a procurement and solicitation page where you can find many other projects as well.
All right, and one final one we'll take. You mentioned that you support compliance to DO-178, things like code coverage. Do you support object code verification per DO-178C level A?
Yeah, good question. Yes, we automate object code coverage with our ASM tool solution that we offer. We automatically generate coverage from executable object code, and we can do this on target hardware or your desktop development or simulation environment.
Okay, so thanks once again, Ricardo. Thanks everybody for attending. If you've got further questions, again, please send them to us, info@parasoft.com. We'll be happy to answer them for you. If you have suggestions for other topics you'd like to hear about, or if you'd like to know more about any of these topics, please let us know. And there will be a recording available for you to watch, and you'll get an email that gives you all the details. So thank you, everybody, and have a great day.
Thank you. Bye-bye.